Thank you for attending today's webinar. Tanner EDA's HyperSilicon is a complete IC design suite that allows you to speed from concept to silicon for analog and mixed signal designs on the PC or Linux platform. The tools are powerful, easy to use, and easily complement and interoperate with other flows. I'm Jeff Miller, Product Marketing Manager for the Tanner EDA group here at Mentor Graphics. And in today's demonstration, I'll be focusing on our HyperSilicon design flow and show you how to use the design flow along with add-on products like HyperDevGen, HyperPX, and talk a bit more about digital simulation in our digital flow. This demo is designed to take you through our design flow. Let's talk about the design flow a little bit first. This is Tanner EDA's flow, and as you can see, down the left side we have a complete analog design flow. And down the right side, we have a complete digital design flow along with some mixed signal portions. So I'll go through each box here. First, you have schematic capture and design entry in SEdit, which is our front-end design cockpit. Second, our SPICE simulator, T-Spice, handles analog simulation. We do our digital simulation work in ModelSim, and mixed signal analysis using T-Spice and ModelSim in a co-simulation environment. Once the design part is finished, you proceed to layout. LEdit is our physical layout tool. We also have physical verification in either Hyper Verify or Calibre, and post-layout simulation using HyperPX or Calibre XRC. On the digital side, we do our synthesis in Incentia's DesignCraft. We use LEdit for the place and route using HyperPNR, and then functional verification using ModelSim for dynamic timing analysis and Timecraft for static timing analysis. Once the digital block and the analog block have been completed, we proceed to mixed signal assembly, so put down your digital block, your pad frame, your analog blocks, and route them together using our chip assembly auto router. And finally use Calibre or Hyper Verify to do the physical verification and do a final mixed signal simulation using our T-Spice and ModelSim co-simulation environment. So that's the design flow in a nutshell. Let's have a look at the tools. HyperSilicon has schematic entry for IC design and handles the latest IC design challenges. SEdit's easy to use and integrated with our analog simulator, which means you can run simulations, view DC operating point results in your schematic, do waveform cross-probing, all without leaving the schematic editor cockpit. Designs can be exported for simulation, LVS, schematic-driven layout, etc. So here we have the test bench for an 8-bit successive approximation ADC, which will serve as a simple example for our demonstration today. A quick tour of the layout of the interface. We have our library navigator here where you have any libraries in your design. Inside the library we have cells. Cells can have multiple views, so I can have a schematic view, a symbol, or in some cases, say, a Verilog AMS view. The schematic part is in the center here, and then off to the side are the property navigator where I can edit the properties of any object in the design. This is a test bench, but I can double click to descend down into the design. So I can double click to go down and pop back up. I descended into a module that's implemented using Verilog, pop back up to schematic. So we have a complete cockpit with multiple view types. Node highlighting is supported across the hierarchy, so if I highlight a node here and pop up in the hierarchy, you can see that it's still highlighted. SEdit also has a number of features around arrays and buses. Here you can see a bus for the binary output value, which of course is an 8-bit bus on an 8-bit ADC. Proceeding to simulation, our analog simulator is T-Spice, and if you recall, our ADC is implemented using a DAC, a comparator, and a digital control block implemented in Verilog. So we'll need to do a mixed signal simulation in order to capture its behavior. I go ahead and invoke T-Spice using the T-Spice button over here. That will automatically launch T-Spice and open up my design. So it's exported this netlist automatically, inclusive of Verilog A, Verilog D, or Verilog AMS views, along with Spice, and all the simulation commands necessary to run a simulation. I've configured the tSpice to run the digital simulator in GUI mode so we can interact with ModelSim while the simulation runs. So as I invoke the simulation, tSpice will automatically analyze the netlist. It's going to find any Verilog D or Verilog AMS views and automatically load those up into ModelSim, compile them, load the simulation environment, and pop up ModelSim. So now ModelSim is up. The simulator has moved to the DC operating point and it's ready to start the simulation. So I'll step over to ModelSim, configure things. I'll go ahead and add a few signals to the waveform here, and then I'll tell ModelSim to run the full simulation. In the background, what's happening is ModelSim is running and tSpice is running in the backgrounds, and they're communicating the signals that cross the mixed signal boundary. So the analog signals that touch the digital will appear in WEdit, and this digital signals are all appearing in ModelSim. So over here in ModelSim, if you show the whole thing, you can see all my digital waveforms in traditional digital representation, boxcar diagrams, etc. And over in WEdit, you can see more of the analog behavior of the design. So I can analyze my design and get a better idea of what's going on there. WEdit is our complete waveform analysis package. It supports cross-probing. It's fully integrated with SEdit and supports cross-probing of signals. And it's really a complete analog waveform analysis package. Taking a quick tour of the user interface, we have all of our simulations over here. We have our traces over here, so all the traces that were present in the analog portion of the design. And down below we have our waveform calculator, where we can do a number of advanced measures of the waveforms. So here you can kind of get a feel for the very wide breadth of analysis modes available in WEdit. This is LEdit. By way of a quick tour of the user interface, we have our library navigator. Docked behind that is our layer palette with all of our layers and layer purpose pairs. Here we have schematic driven layout navigator, and behind that our verification error navigator for DRC and LVS errors. Finally, we have our command line where you can type tickle commands. All of the windows, or the toolbars in LEdit are dockable, so I can move these things around. I can dock it behind, I can place it next to, so I can fully customize this, the user interface to my liking. I'd like to give a quick demonstration of how the schematic-driven layout flow works in LEdit. So we start with a netlist. So I'll go ahead and bring in the Import Netlist dialog box. Here we have the name of our Spice deck. This is Spice file comes straight out of SEdit, or I can directly transfer the design from SEdit. So I'll go ahead and read the design in. What's going to happen is LEdit reads the design, locates any parameterized cells that are needed, generates those with the correct parameters and instances them in the layout, and then places things roughly in the proportion they were in the schematic, which allows me a leg up in getting started. I'll go ahead and show some flylines. So the flylines are supported here. You can highlight various nets in different colors. I like to highlight a whole bunch of them so I can kind of get a sense of where things go, and then I can start doing a placement. So just kind of move things around. The flylines update in real time as I move my cells until I get to the point where I am happy with the placement. Then I can move on to routing. Let's clear these flylines here. LEdit is a full custom layout editor, so I can draw objects using a number of very productive tools. LEdit is a particularly fast and flexible layout editor. LEdit has a number of features that make layout editing quick and easy. One of the key features is the interactive DRC. So I'll go ahead and enable that. Interactive DRC checks a simple set of design rules as I'm editing the layout, which allows me to very quickly do DRC correct layout without doing a lot of zooming in and drawing of rulers. So if I draw a polygon here, and then I can draw a second one. As I approach the polygon, you can see that the marker turns red, indicating that I have reached the limit, and if I continue getting closer, you'll see a red marker indicating that I've made a DRC error. So here you can see it a little better as I zoom in, but there is the at the limit, and now you can see it turns red. Now if I want, I can also enable mode where it prevents violations. This allows me to do very quick layout where I can draw until I get to the limit. It's going to stop me, and then it finally makes the connection as I make it across. So this way I can generate DRC correct layout really fast without doing any zooming in. Another great feature of EditIt is the object snapping. When I enable that, it's going to allow me to automatically lock on to nearby layout objects and similarly achieve very high layout speed. So in this case, if I wanted to draw metal that perfectly aligned with these corners, I can turn on the vertex locking, and as I approach, I see a cursor marker indicating that if I click, it's going to lock onto that location. And similarly on the other end, so I can very quickly draw correct layout without doing a lot of zooming in or measuring things and stuff like that. So this can be really handy. We can lock onto different kinds of devices. So if I choose, I can lock onto midpoints, I can lock onto edges, I can lock onto intersections, and you can toggle each of these on and off at any given time. You can also lock onto text objects, which of course makes it easy when you're doing routing. Etc. So this gives you an idea of how our analog design flow works. Now let's move on and take a look at how the digital side works using the Hyper Place and Route tool. So I'm going to switch designs over to the digital design now. So this design represents the logic block from our successive approximation ADC. The interesting thing about this design is that it's an open access design. Open access is a layout database format that EditIt fully supports, which is also supported by a number of other tools on the market, which allows us to easily interoperate into flows supporting open access tools. So I've gone ahead and opened up the design, and you can see we have our layers, etc. So I've gone ahead and opened up my ADC control block. Here we've got just a very basic layout. We have a bounding box which defines the area I want my placed surrounded block to fit into, and I have a few I/O ports down at the bottom, the actual inputs and outputs of my digital block. The next step is to import the Verilog netlist into SDL. So I went ahead and synthesized the design using Insentia's DesignCraft, and this is the synthesis result. So now it's been compiled down to the gate level, and we're ready to proceed to place and route. So I'll go ahead and import that netlist. It's going to fill in the SDL navigator with all of the netlist information, and now I'm ready to start the place and route process. The first thing I need to do is fill this in with placement rows. So using this menu, I'll go to Placer and Fill Shape with Rows. What's going to happen, I'm going to choose the standard cell that I want to use for placement. In this case, I'll use the core cell. I'll grab the core cell and fill it in. It adds 672 sites, and now I have my placement grid defined. So now I'm ready to run the placer. Our placer is fully left and def based, so I'll bring in the left files for my technology, for my standard cells. I'll give it some parameters, potentially, and tell it which cell views to use for the abstracts. So once I'm ready to go, I'll say placer and run placer. The placer is going to put down all the digital cells on the design. It's going to optimize that using simulated annealing algorithm, so then I can watch its progress as it goes. So as it goes through its placement process, and now it's complete. So I can look at the placement, inspect it, make sure it's all what I want it to be, and then move on with the process. The next step is to insert the filler cells. Although we have a clock router, so we should look at that quickly. Basically, the clock router splits up large nets like clocks into balanced trees so that you have low skew in your design and don't have hold time violations. This design is small enough that it actually doesn't need a clock tree, so I'll just go ahead and clear that. Once you've done your clock tree insertion, you need to insert filler cells to fill in the rest of the design. I'll just accept the defaults here, and it's going to fill it in with either a mix of decoupling capacitors and just row fillers in order to connect up all the power and ground rails. The power and ground rails are connected across the rows, but we still need to connect them using power stitching down the sides. So for that, we'll place the power rails. We can set this up to set the rails, whether they're on the left or the right, how thick they are, etc. We'll just go with the defaults for today. So now I have my power and ground rails, I've got my placement, and I'm ready to proceed to routing. Our router is an N-layer full over the cell router based on the rules in the left and def files. It has bus routing optimization, some other features for chip level assembly, but for now we'll just run it in the default mode. I'll go ahead and hit the route all button. This is going to route all the signals from the ports that we placed down below into the cell area, and of course all of the nets within the cell area. And now it's complete, and the design has been fully routed. So we have a complete placed and routed block. So now we can do some timing verification by extract and write SDF. This will take write an SDF file based on our PDK's Liberty files for the fast, slow, and the typical fast and slow process corners. Write out an SDF file that then we can take into static timing analysis in Timecraft or dynamic timing analysis in ModelSim. So that completes the digital flow, and now we're ready to do top-level chip assembly. For top-level assembly, I'll switch over to the top-level context of my design. Open up the top-level cell. So here we have the logic block, which is just a large array of logic, a RAM block, and the ADC that we've been working on, along with a pad frame. Now this has a large number of signals. I can highlight those real quick to give you an idea. And these are all fairly simple, straightforward routes, but it would be a real hassle to route all these by hand. So instead, we can use our chip assembly router. So I'll go ahead and tell it to route all. This is using the same basic routing technology and same design rules and setup as the logic router, and now just running in a chip assembly mode. So it's going to go through, it does a global routing pass to do sort of a high-level broad routing, and then it does a detail routing pass, goes through, and assembles the design, and it's complete. And so this saves a lot of time during the chip assembly process. Now that the chip is fully assembled, it's time to move on to physical verification. For physical verification, I'll switch over to a slightly smaller cell. Let's take a look at here. So here's a cell, and I'll go ahead and create an intentional design rule error so that we have something to look at. So here's a likely width rule and a likely spacing rule. And so I'll go ahead and run DRC. Hyper Verify is our physical verification tool for DRC parasitic extraction and LVS checks. I can set it up here. It's going to give me an option option to check or uncheck all of our design rule decks. Now we can do simple DRC decks using our graphical user interface to build up the decks, or we can use the decks that are provided by the Foundry in a textual format. I'll go ahead and invoke the DRC, so I press the DRC run button. In the background, it's going to fire up Hyper Verify, which is our verification tool. It's going to run through the design, export the design, run Hyper Verify, check all of the design rules, and then return the results back down into my DRC Error Navigator. The Error Navigator is hierarchical, so it can see errors in the cells as well as zoom to the cells, jump to location. So as I go through, I can see what rule I violated and see the marker on the screen. I can move through these and see all of the errors that have quickly look at the errors, realize what's going on, check them off as I fix them, and move on to the next thing. So once that's done, I can do an LVS check, and then I'm ready for tape out.